That's all, by definition, we ever tell digital computers how to do. And so digital computers are inside the Chinese room in a certain sense. Today we're talking about John Searle's famous, super famous Chinese room thought experiment. Since it's a thought experiment, that just means that it's an imagined scenario, a scenario that you have to imagine, and once you imagine it, Searle thinks you're going to get a certain kind of imaginative result, and that's going to prove something about a certain theory of the mind. And if you're going to understand the philosophical theory of mind that this thought experiment is trying to disprove, then we need to do a super quick recap of the theories of mind that we've talked about in this course, and so I'm going to write some stuff up on the board now. So these are the theories of mind that we've already talked about in this course. You can go watch my previous videos to get a recap of all of this sort of stuff very quickly. Dualism is the theory that the mind and the body are different kinds of stuff. They're distinct. There's two kinds of things in the universe, mental stuff and physical stuff. Behaviorism, identity theory, which is short for the mind-brain identity theory, and functionalism, these three, they are all versions of physicalism, which is the view that there is only physical stuff in the universe. The only things that exist are physical things, and so the mind is just part of the physical world. Behaviorism is the version of physicalism that says that the mind is just behavior. Identity theory is the version of physicalism that says the mind is identical to the human brain. And functionalism is the version of physicalism that says that mental states or mental processes are just functional states or functional processes. Functions, you'll remember, and this is the most important thing to catch up on, so I'll put in the description the link to the video about functionalism. Functions are defined in terms of causal inputs and outputs. That's going to be important for what we're talking about today. Before I can say what the Chinese room thought experiment is, we need to just understand what Searle's target of attack is, the thing that he's attacking. It's a theory of mind that he calls strong AI. Strong AI is short for strong artificial intelligence, and this is a theory about the human mind. As Searle understands this label, which he is introducing, strong AI is the theory that the human mind, all of your thoughts and memories and beliefs and desires and feelings and sensations, all of that stuff that make up your mind, the human mind is a program that's being run on the brain. Just in the same way that there's some software, there's an application or a program being run on the hardware of a computer. So according to this theory, the mind is the software and the brain is the hardware. That's the theory that Searle is attacking, and here's what he says about that theory. This is on page 669 in the reading, if you're following along. This view, that is strong AI, has the consequence that there is nothing essentially biological about the human mind. The brain just happens to be one of an indefinitely large number of different kinds of hardware computers that could sustain the programs which make up human intelligence. On this view, any physical system whatever that had the right program with the right inputs and outputs would have a mind in exactly the same sense that you and I have minds. So, for example, if you made a computer out of old beer cans powered by windmills, if it had the right program, it would have to have a mind. And the point is not that, for all we know, it might have thoughts and feelings, but rather that it must have thoughts and feelings, because that is all there is to having thoughts and feelings, implementing the right program. If you've been taking this course up until now, you should recognize strong artificial intelligence. The idea that having a mind just is running a certain program defined in terms of inputs and outputs, right? That theory should seem familiar to you because it's one of the theories that we've already been talking about. It's this one. It's functionalism. Strong AI is a version of functionalism. The idea is simply that if you have the right functional structure, you take the right inputs and give the right outputs, then you are a mind, or then you have thoughts and feelings and desires and emotions and sensations and so forth. If you think it's possible to take a human mind, take all of a person's memories and thoughts and that sort of thing, and download them onto a computer. If you think that's possible, then you are an adherent of strong AI, this version of functionalism. And what Searle is going to do when presenting this thought experiment is he's going to attack that theory. He's going to say that theory doesn't work. That's not the way the mind is. One last thing before we get to the thought experiment itself. Here's just another passage from the reading. This is on page 670, and it's just some characteristic John Searle snark. This is just him saying that there really are scholars, theorists, researchers, whatever, who actually believe in strong AI. Here's what he says. Herbert Simon of Carnegie Mellon University says that we already have machines that can literally think. There is no question of waiting for some future machine, because existing digital computers already have thoughts in exactly the same sense that you and I do. Well, fancy that. Philosophers have been worried for centuries about whether or not a machine could think, and now we discover that they already have such machines at Carnegie Mellon. That's some classic John Searle snark, which we're going to put aside for a minute so that we can talk about what he means by the terms that he uses in this reading, syntax and semantics. Let's start with syntax. The word syntax just means grammar, right? So the English language has certain rules of grammar that say that the verb has to go here and the noun has to go there and you put a comma here or whatever. Searle is using the word syntax in a broader sense to refer to all of the formal features of some language. Here's an example to illustrate this. I'm going to write a word on the board that I assume you don't know. Okay, so I needed a language that doesn't use the same alphabet as English, and so I've got this word here, right? You don't know what this is. I do, but let's say you don't know what it is. You can know lots of things about these symbols right here, right? Like, you know that like this symbol right here is taller than the other symbols, right? This one, you know, it's like taller. It's like up here to down here, whereas this symbol only goes up to there, right? And this one is sort of a straight line, and there's a dot over it. I could have left the dot out, and then this one is sort of like a swoopy thing that looks like the English letter E. You can know all sorts of stuff about these symbols without knowing their meaning. You know something about their form, their shape, right? Those formal features, the features that have to do with their form, that's what Searle means by syntax. All the stuff like the order in which the symbols appear, you can understand that, right? If I were to switch the symbols around in order or write one on top of the other instead of next to the other, all that sort of stuff, you could understand that without understanding the meaning. And so all of those facts about these symbols fall under the category of syntax for Searle. Then there's the actual meaning of these symbols. These symbols aren't just some shapes, they're a word in a language. They're the word shalom in Hebrew. This is Hebrew. I wrote this on the board. Shalom is the Hebrew word for peace. It's also used as a greeting. You use it to greet someone. You say hello, shalom. Sometimes you also say goodbye by saying shalom, but I think less frequently. It's mostly used as a greeting when you first encounter someone to sort of mean hello. This is a Hebrew word, and now you know the meaning of it. The meaning is the semantics. Semantics just means the meaning of it, what this word represents. It represents the idea of peace. Okay, so do you understand the difference between syntax and semantics as Searle is using these terms? The syntax are the formal features of the language, the shape of the letters and that sort of thing, the order in which they appear, that sort of stuff. And then the semantics are the actual meaning, the content, what these symbols represent. The shapes of the symbols, their form, and what the symbols represent. Syntax and semantics. Okay, we're almost there. We're almost ready to talk about the Chinese room thought experiment, but not quite. First, we need to introduce the idea of a digital computer. And to understand what we mean by digital computer, we have to talk very briefly about a guy who lived in England in the middle of the 20th century named Alan Turing. Turing was a mathematician and computer scientist living in England. There's a movie about him. Benedict Cumberbatch plays Alan Turing. I don't love the movie, but it's fine, I guess. Whatever, there's some problems with it, in my opinion. The point is, this dude invented computer science, invented computers, used the computers to crack the Nazi Enigma code, defeated the Nazis, and then, later in his life, because he was gay, the government of the United Kingdom forced him to get electric shock therapy to cure him of his homosexuality, which drove him to commit suicide. So not a happy ending. There are a lot more interesting things to say about Alan Turing, the person, but we're just going to talk about a certain kind of digital computer, a theoretical computer called a Turing machine. A Turing machine is a theoretical type of machine, although actual computers are, in some broad sense, all real Turing machines. But here's the way to think about what a Turing machine is, and this is a little bit oversimplified. Imagine you've got a piece of tape. It's a long piece of tape, and the tape is split up into cells, little units or whatever. And on each of these cells, there are some symbols written. In fact, there are not just any old symbols. There are digits, and there's only 2 digits written on these, right? Either the digit 1 or 0. This is where binary code comes from. There's 2 digits, there's only 2, bi, right? There's 1s and 0s. And this code can be used to represent all sorts of stuff. The Turing machine is this piece of tape plus a little thing, we'll draw it with like little wheels. It's like a little box with wheels on it, right? And this little box, it can drive along the tape from one cell to the next one and so on. It can go backwards and forwards, right? And it can erase whatever's inside the cell, and it can write either 1s or 0s in there. And different Turing machines can run different programs, but we're going to imagine that this Turing machine is an adding machine. It adds up numbers. So here's what's going to happen. We feed into the machine this piece of tape. We've got 3 1s, and then a 0, and then 2 1s, and then 3 0s, right? This adding machine is going to add these numbers, right? So we've got the number 3, 1, 2, 3, and then we've got a space, and then we've got the next number, 1, 2, 2. So if this machine does its job right, then it's going to add 3 and 2 and get the answer 5. Here's how the machine works. The machine doesn't know that these 1s and 0s represent numbers. It doesn't know anything about numbers. All it knows is that when it sees a 1, it ignores the 1 and moves on to the next cell. And it sees another 1, it can read the 1 and it says, nope, moving on to the next cell. Remember, it doesn't know that this thing is called a 1 or that this one is called a 0 or anything. No. It can just recognize the syntax. It can just recognize the shapes of the symbols and perform functions as a result of that. It doesn't know the semantics. It doesn't know what any of this means, right? It doesn't know that this is a 1, it represents the notion of 1, or that these 3 1s put together represent the number 3. It doesn't know anything about the meanings of these symbols. It just can respond to their form or their shape. It can follow instructions. Okay, so it sees the 1, it keeps going. When it gets to the 0, it sees a 0. And it has some different instructions for what to do when it sees this round 0-shaped thing. When it sees a round 0-shaped thing like that, it erases what's on the cell. And it replaces it with a 1. Those are the instructions. Just erase the 0, replace it with a line. Okay? And then it switches itself into a different internal state. Things get a little complicated. We don't need to worry about that too much. But then it knows it just keeps going. It sees a 1, it keeps going. It sees another 1, it keeps going. It hits its second 0. When it hits the second 0, it's got instructions for what it's supposed to do. It's supposed to go back 1 spot. So it's got little wheels, it just backtracks again. And then it has as its instructions to erase the symbol in the cell that it goes back to and write in a 0. And then its last instruction in here is to halt. Halt means stop. That's all that the Turing machine did. It just looked at some symbols, moved to the next one. Sometimes it erased, sometimes it didn't understand the meaning of anything that it was doing, but look what it did. It produced the correct answer. 5. 1, 2, 3, 4, 5. 5 1s in a row represents the number 5 in the system that we're using, in the language that we're using. So even though this damn machine didn't understand anything about addition, didn't know anything about numbers, didn't have any meaning or semantics at all, no semantic understanding of any kind, all it could do was manipulate symbols, but nonetheless, it successfully added 3 and 2 by just following some basic instructions. That's what a Turing machine is. Computers work this way. They manipulate symbols. At least the computers that are, well, digital computers that run on binary code, they just take strings of 1s and 0s, very, very long strings, and they move the symbols around. That's it. The key point is this. A digital computer is a very specific type of thing. All it is a digit manipulator. All it is a device that moves around symbols. That's all it does. That's all it ever can do if it's going to be a digital computer. Now we are ready. We're ready to get to the famous Chinese room thought experiment. What this thought experiment is going to try to show is that strong AI is false, and thereby that functionalism is false, right? And it's going to show that by showing that a digital computer can't understand the meaning of anything. Computers like this that just manipulate symbols, they can have syntax, but they can never have semantics. So they can't have human understanding. They can't have thoughts in the way that human beings have thoughts, because our thoughts involve the understanding of the meanings of symbols. This should all become clearer. I'm going to read a long passage which explains the Chinese room thought experiment. This is on page 671 if you're following along in the reading. Imagine that you are locked in a room, and in this room are several baskets full of Chinese symbols. Imagine that you, like me, do not understand a word of Chinese, but that you are given a rule book in English for manipulating these Chinese symbols. The rules specify the manipulations of the symbols purely formally in terms of their syntax, not their semantics. So the rule might say, take a squiggle sign out of basket number 1 and put it next to a squoggle sign from basket number 2. Now, suppose that some other Chinese symbols are passed into the room and that you are given further rules for passing back Chinese symbols out of the room. Suppose that unknown to you, the symbols passed into the room are called questions by the people outside the room, and the symbols you pass back out of the room are called answers to the questions. Suppose, furthermore, that the programmers are so good at designing the programs and that you are so good at manipulating the symbols that very soon your answers are indistinguishable from those of native Chinese speakers. There you are, locked in your room, shuffling your Chinese symbols and passing out Chinese symbols in response to incoming Chinese symbols. On the basis of the situation as I have described it, there is no way you could learn any Chinese simply by manipulating these formal symbols. Okay, so let's draw the scenario as Searle is imagining it. So we've got a room, and then we've got a person in the room, right? And the key thing is just that this person doesn't understand Chinese, but does understand English. What we have here are some pieces of paper. And on the pieces of paper are some symbols in Chinese or Hebrew or Arabic or one of a gazillion other languages that you inside the room don't understand. You don't understand the semantics, but you can still understand the shapes, the forms, the syntax. So we've got some symbols on there that you don't understand. And these pieces of paper get passed in through a slot. And inside the room, you have a rule book. And the rule book has some instructions on it. And the instructions just tell you how to manipulate symbols, the same way that computers manipulate symbols. When they see 1s and 0s, they erase some of them, they replace some of them, that sort of thing. All these instructions ever do is tell you how to deal with the syntax of these symbols. They never tell you what the symbols mean. And you look up in your rulebook, it says when you get a symbol like that, you should pass out a piece of paper that has a symbol like this. Searle's point is this. You can get very good at this. You could get very good at recognizing these symbols and knowing what page the rule is for that symbol in the book, so you could do it very quickly, and you could become very accurate, always passing out the symbols or the whole series, a long series of symbols, right, that you're supposed to pass out of the room whenever you get this sort of input. You could do this for 1,000 years. You could think really hard, you could be a super genius in there. You would never be able to figure out what these symbols mean. No matter how many symbols you processed, following your rule book, reading every word of the rule book, which is 1,000,000 pages long, and you can fit it all into your brain, doesn't matter. You're never going to be able to figure out semantics from syntax. I mean, think about it. I'm assuming that you didn't know Hebrew. You could never figure out the meaning of these symbols just by looking at the symbols and seeing how tall they are, or seeing, which other symbols get spat out when these symbols come in. There's no amount of information about the form of symbols and how those symbols are supposed to be manipulated that could ever tell you the meanings of those symbols, no matter how smart you are. That's Searle's point. And Searle's point, moreover, is that if you think about it, that's the situation that a digital computer is in. We never teach digital computers because of the definition of what they are as digital computers. They're just symbol manipulating machines. We never give them anything other than instructions about how to manipulate symbols, which zeros to erase and replace with ones, and which ones to erase and replace with zeros, and how to move around the symbols. That's all, by definition, we ever tell digital computers how to do. And so digital computers are inside the Chinese room in a certain sense. They're just given information about how to manipulate symbols, and they get lots of practice manipulating symbols. But they're never given any information they can't be, given the type of things that they are. They're never given any information about the meanings of those symbols. And so therefore, digital computers can't understand languages. They can move symbols around in languages, but unlike human beings who understand the meanings of words, computers, digital computers, never and never could understand the meanings of words. And so there's this thing, there's this mental state, this state of the mind, we could call it understanding. And that's a state of the mind that a mere functionally described machine could never have. According to Searle, if we interpret the Chinese room thought experiment in the way that he wants us to interpret it, it shows that digital computers can never have understanding. Now, notice here that there's a difference between a digital computer, which is a rather specifically defined type of machine, and just machines in general. Searle is not saying that we could never build a machine that had understanding and consciousness and thoughts and whatever. That's not what he's saying, because indeed, in a certain sense, maybe the human brain is a machine. If we understand machine in the broadest sense that it can be made up out of brain goop and neurons and whatever, then sure, machines could have thoughts, machines could understand things. But Searle's not talking about machines in the broadest sense, such that the brain, the human brain, is a machine also. No. He's talking specifically about digital computers. And he's saying that digital computers can't have thoughts. And the reason that they can't have thoughts is because they are just syntax manipulating machines, and syntax is never enough for semantics. Or, to put it another way, form is never by itself sufficient for meaning. Okay, so that's his point. Computers, as we have them, all of the computers that we have, which are digital computers, they can't think. Here's something that Searle says to sort of make this point directly. This is on page 673 in the reading, if you're following along. Is instantiating or implementing the right computer program with the right inputs and outputs sufficient for or constitutive of thinking? The answer is clearly no. And it is no for the reason that we have spelled out. Namely, the computer program is defined purely syntactically. But thinking is more than just a matter of manipulating meaningless symbols. It involves meaningful semantic contents. These semantic contents are what we mean by meaning. Okay, so the thought is functionalism is false, because having the right inputs and outputs is just a matter of syntax. A digital computer that has all the right inputs and outputs, that kind of computer, all the computers we have, they can simulate understanding of the Chinese language, for example, but they can't actually have understanding because all they ever get, like the person inside the Chinese room, all they ever get are facts about syntax. They never get any information about semantics. As just a last little thing, we should talk about one response to the argument that Searle is making that says that Searle is just getting it wrong, and that's called the systems response. The idea behind the systems response is that, sure, Searle's right. This dude inside the Chinese room, he can't ever understand Chinese. But the thing that is understanding Chinese, according to the functionalist, according to the strong AI theorist or whatever, is not a person inside of the Chinese room. It's rather the whole damn system. This whole system is the thing that understands Chinese. There's no part inside the system that understands Chinese. Of course, that's true. But understanding Chinese just is being a system that does all of this. If there was a person inside of a Chinese room, and that person could take in Chinese symbols as inputs and give the right Chinese symbols as outputs, then, according to this response, that whole system, not the person inside, that whole system would understand Chinese, because that's all there is to understanding Chinese. Searle considers the systems response in the reading that we read for today, in the original article about the Chinese room, and here's what he says about the systems response. You can judge for yourself whether or not you think this is an adequate response. This is on page 672. Some people attempt to answer the Chinese room example by saying that the whole system understands Chinese. The idea here is that though I, the person in the room manipulating the symbols, do not understand Chinese, I am just the central processing unit of the computer system. They argue that it is the whole system, including the room, the baskets full of symbols, and the ledgers containing the programs, and perhaps other items as well, taken as a totality that understands Chinese. But this is subject to exactly the same objection I made before. There is no way that the system can get from the syntax to the semantics. I, as the central processing unit, have no way of figuring out what any of these symbols means, but then neither does the whole system. Okay, that's Searle's response. The point is, it doesn't matter if you include the whole system. The whole system is just a symbol manipulating system, like a digital computer. But symbol manipulation is never enough for actual understanding. It's not crazy. That kind of seems right, and if that's right, then strong AI is false, and maybe as a result, functionalism in general is also false.